Hello everyone, welcome to this webinar on flood barriers. Today we have two speakers for you. First we have Omar Saleh. Omar is the director of Zephyr Consulting. It's a company that offers a variety of flood and drought resilience solutions, including innovative mobile flood barriers. Omar has a lot of experience in the water sector and holds a Master of Science degree from the University of Amsterdam. He has lived and worked in many countries such as UK, South Korea, Singapore, and Omar enjoys traveling and visiting new countries, and especially when he can implement projects to mitigate the risk of flooding and drought. He's looking forward to sharing his experience with you today. Next to Omar, we have Martine Rottink. She is a consultant, integrated water management at Nederlands Schuurmans. She has a background in hydraulic engineering in Delft and experience in modeling, both for water system analysis and flood risk studies. My name is Jonas van Schoonsen Landman. I'll be the host for the webinar today. Before I give the word to Omar, first a few practical issues. If you have any questions, there is a chat on the right-hand side. You can ask questions. We will address the questions after the webinar, after the presentations are finished. Do you have any problems with IT, or you're being locked out, or you have issues? Don't hesitate to call me. My phone number is here on the screen. So first, I would like to give the word to Omar. He will present the use of flood barriers. Let me see if I stop sharing my screen, and I'm making you presenter. If all is well, you can now present, Omar.
Yeah.
All right.
Yeah, you can see my screen.
Perfect. Go ahead.
Thank you all. First of all, thank you, Nederlands Schuurmans, Jonas, for inviting me for this webinar, and participants, welcome and thank you for joining. Today I'll be giving a presentation about our organization. What we offer is innovative solutions to enhance resilience to flooding. In particular, a mobile flood barrier called SlamDam. So my name is Omar Saleh, indeed what Jonas mentioned, the director of Zephyr Consulting. I also represent MWD, or SlamDam BV, that offers this particular mobile flood barrier. What I want to do today is give you an overall picture of mobile flood barriers, the projects that we do, and the challenges we face, and how IT supports our projects. So mobile flood barriers are relatively new. We've seen things like sandbags already now for decades, but I'm talking more about the more advanced mobile flood barriers. Compared to permanent solutions such as drainage systems, excavation or widening of riverbeds, nature-based solutions, there are some advantages. Even though nature-based solutions have become very popular the last decade. But if you look at mobile flood barriers in general, I think the big advantage is that there's no encroachment. So what happens normally with infrastructural projects, people might need to migrate, or it impacts the land of people, and that leads to resistance. While mobile flood barriers have a higher acceptance rate. It's also a lot more useful for unexpected situations. And this is important because of things like climate change, urbanization. What happens with permanent solutions is that they are, for them, it's a bit more challenging to adapt to these changes, and mobile flood barriers can adapt with, for example, urbanization. There's also an easy and rapid installment of mobile flood barriers. It doesn't take years. For example, with nature-based solutions can take up to 5, 10, 20 years before them to be fully developed. Mobile flood barriers, you ship them to the location and they are able to deploy it immediately. And in addition, it's also important to build independent resilience. What I mean with that is that what we try to do with our projects is give communities, because quite often these are community-driven projects, give them the tools and the capacity to enhance resilience to floods and drought independently. I was saying there are some advantages with regards to mobile flood barriers compared to other solutions. What we offer is a water-filled flood barrier. Let me skip to that straight away. Our solution is called Slam Dam. Slam Dam has a unique design and material combination. It's made out of EPDM, which is a synthetic rubber, and it has some unique properties. It's UV resistant. You can store fluids vapor tight, and it's very durable. So it has a lifespan of more than 40 years. And even after the 40 years, it's 100% recyclable. Slam Dam consists of 2 compartments that have to be filled with water. You do that using a pump and a hose. That can be done very quickly, very easily. And we have standard models, but we can also make tailor-made solutions. Another key advantage of a solution like Slam Dam or mobile flood barriers in general is that it's easy to use. So people don't need any advanced degrees or technical backgrounds. You see here in the pictures how it's deployed normally. You store it in stackable boxes. You take the boxes to the location when there's a threat of flooding or when you want to deploy them. You connect some hoses to them and a pump, and then very rapidly you can build up a barrier. Depending on how many people you have, how many pumps, you can build up a barrier of kilometers in a matter of hours. And when the risk has subdued, or when you want to store the Slam Dam or the mobile flood barrier again, you just deflate them and roll them up, put them in the boxes, and store them in the facility. It's also a multifunctional solution. You can use it, like I mentioned, to store fluids. You can use it as a bridge, in which case you need to fill it with air. You can use it for chemicals and oils, but also to control water availability for agricultural purposes. And what we've seen an increase in demand for mobile flood barriers the last couple of years, especially in developing countries. We've completed various projects in Africa and Asia, now also in Fiji. And normally how we work closely with Nederland Schuurmans, luckily. And we have a standard project approach that consists of 6 phases or 6 work packages. Obviously, there might be some customization per project, but roughly you can say that we follow these 6 work packages. So first we start off with the project inception to set the boundaries and the scope of the project. Then we have the second phase where we have the flood and risk and benefits assessment, followed by a monitoring evaluation where we figure out, okay, how are we going to monitor the impact and the results of deploying a mobile flood barrier. Then we manufacture the flood barrier, ship them to the location and train people and give a demonstration. Quite often a demonstration is part of the training. And then the final phase will be project closure. And what we see in our projects is the red circled activities. These are often the most important, but also the most challenging activities and parts of our projects. Luckily, we work at Nederland Schuurmans. Without them, we would be completely lost, I think. But what we do in this phase with these activities, we try to analyze the flood risks or drought risk in a particular area. We do this via data collection, which can be very challenging in environments where there's no data-rich environment. That happens often in developing countries. We try to develop flood scenarios and determine the adaptation benefits that I'll explain later on. And then hopefully what we try to do is select the location where we would deploy the mobile flood barrier, and also the dimensions of the flood barrier. What should be the length? What should be the height? So this is normally how we work in a project. I can show you with a few examples. So this is a project we completed last year in Burundi. Was for the United Nations. What happened in that area in Burundi is the people there suffer from flooding caused by rising water levels that destroys crops, impacts the communities. So that's a big issue in Burundi and leads to food insecurity. What we did over there in the first phase is we analyzed the flood risks in a particular area. So we used the state-of-the-art software from Nederland Schuurmans for that. This gave us an idea of the flood characteristics, like what is the flow velocity, what is the direction of the water, what is the flood depth. This in combination with field visits, so we have a local partner who explored the area. This gave us an idea of, okay, what are possible locations where we can deploy a mobile flood barrier? And here you see the orange lines. these locations seemed suitable for deployment of a mobile flood barrier. We selected only one, by the way, out of the 4 because was still a small scale project. But eventually, when we had the location in mind and we knew the dimensions of the mobile flood barrier, we manufactured it, shipped them to the location. We trained the people, like in less than half a day, the people were equipped on how to deploy the mobile flood barrier. And now they are using it to prevent flooding. So I think in this case, they will deploy it in March and April. That's the flood season. So they're using it basically as a semi-permanent solution. And what they're doing in Burundi as well, they're using it the entire year as a reservoir to store water and use it for irrigation purposes. Now, we did something similar also in Pakistan. Different environment. I mean, it's in the north of Pakistan where you have glaciers and you have annual meltwater that causes floods. Obviously, we've seen the big floods last year. But this is a project we did last year in Gilgit-Baltistan, where the community is suffering from floods. We did the analysis using the hydrodynamic modeling software, using field visits. This is from our local partner. Again, this gave us an idea of how could a mobile flood barrier help in mitigating the risk of flooding and or drought. But in this particular case, it was all about flooding. What we eventually did, similar to Burundi, we manufactured flood barrier. We shipped them to the location, trained the people, and it worked very well over there. What happens in that area is every day in the summer, in the evening there's flooding because of during the day the sun shines and the glaciers they heat up, and then in the evening you will have meltwater. So in this particular case, I think they used it for 2 or 3 months. They kept them over there, and it proved to be effective. Even now we are doing a project in Fiji, also doing one in Uganda, but this one is in Fiji. And this week we already had a session on where to deploy the mobile flood barrier, what are the flood risks. So we are doing the analysis as we speak. And this is a map of where flooding takes place in that area, where flooding causes damages to people, housing, infrastructure, sugar cane fields, I believe. And now we are exploring, okay, how can a mobile flood barrier help? What should be the length? What should be the height? And we are now in that phase of the project. I referred briefly before to adaptation benefits in one of the project phases, or one of the work packages. What we try to do in the project is we want to determine what is the impact of a mobile flood barrier. And we can do an analysis and we can figure out, okay, is a mobile flood barrier suitable, yes or no? But at the end of the day, not just with mobile flood barriers, but with any flood resilient measures, you want to have an impact. Together with Nederlands Schuurmans, we developed a software tool for that supports that analysis in determining adaptation benefits, as we call them. The tool is called the Flood Intelligence Service, FIS in short. What the tool does, it does a comparative analysis between a flood situation without and with resilient measures or a resilient measure. And there is a difference in damages. For example, in the case of slam dam, mobile flood barriers, if you analyze a certain location and you try to figure out what is the flood damages without a measure, and then you need to figure out, okay, what are the damages if you deploy a mobile flood barrier? And the difference are called the adaptation benefits. And the tool immediately shows you, based on predefined indicators, such as how much damage is there to agricultural land, residential land, how many people are impacted, of whom how many are women, how many are men, elderly, children. The tool gives you insight in that. So this helps us, but also people and other institutions on determining what is the return I can expect of investments in flood resilient solutions. In our case, in mobile flood barriers, but in fact, this tool can be used for any variety of flood resilient measures. So yeah, this, despite the hiccup in the beginning, this is what I wanted to present to you today. I think the main message I want to give is that, yeah, mobile flood barriers have a more important role to play in overall flood risk management. I'm not saying that they should replace other solutions, but I think it's should be part of a holistic approach to mitigate flood and drought risk at certain areas. The challenge always for us is to analyze flood risk and determine the location and dimensions of a mobile flood barrier. Luckily, we have some IT that supports that. And for us, it's really great that we work together with Nederland Schuurmans, and also great to see that they keep on developing and then providing also now a new tool that helps in determining the location and the impact of flood barriers. That's was my presentation for today.
Thank you, Omar, for your presentation. It's very nice to see how this project and how you apply the flood barriers. We have some questions incoming. We will save them for after the presentation of Martine. Martine will present the tool with which we can help determine where the flood barriers can best be placed. Martine, if all is well, you are a presenter now, and you can share your screen. Yes, perfect. Go ahead.
Yeah. Can you see my screen?
Yeah, and now to full screen for the presentation.
Yes. You see the full screen mode?
Perfect.
Okay, perfect. Okay. Okay, thank you. Well, as Jonas already introduced, I'm Martine Rottink. I'm a consultant working for Nederland Schuurmans, and today I will give you a bit more information about flood barriers in 3DI, so the modeling software that we use for water system analysis and flood risk studies, and that Omar just also introduced a bit. Well, I have 3 key points for today. First, I will just give a very short introduction into Nederland Schuurmans and 3DI. Then I will go into an explanation of how flood barriers are implemented in our software, and then give a short demo, a live demo where we can really see the flood barriers in action in our modeling software. Well, first of all, Nederland Schuurmans, we are an independent knowledge firm. We have about 75 colleagues, and we are located in the Netherlands, in the city of Utrecht, of which you can see a picture here in the slide as well. And we also have a small branch office in Taipei. Within Nederland Schuurmans, we have one branch that is focusing on consultancy, and one that is focusing on the development of software and technology. We provide different consultancy services in different fields related to water and IT. They are listed here on the slides as well, but they are mostly climate and environment, urban water management, flood risk studies and operational water management, and also services in the field of water and agriculture. As I already mentioned, we have both a technology and a consultancy branch within Nederland Schuurmans. And within the technology branch, we develop different software products. And our main products at the moment are Lizard, which is a cloud-based data warehouse and analytics platform for the physical environment, in which you can combine different data types as well. So, for example, maps like raster data, time series of measurements, and also vector data, for example, on the location of measurement stations. You can all combine this and also perform some analysis on the data. And our other main software product is 3DI, which is a hydrodynamic modeling software which runs in the cloud. And that, of course, I will tell you a bit more about today, and especially the flood barrier module. We use these software products both in our own consultancy services, but we also make these products available for other organizations and clients as well. So they are also standalone software products. 3DI is our interactive cloud-based hydrodynamic model. It is a model that you can use for hydrodynamic water system analysis, flood risk studies. 3DI solves the full Saint-Venant equations. And within 3DI, we use a special technology which is called subgrid technology, which I will tell you a bit more about in a bit, but it basically enables us to model large areas with a very high resolution while still having a relatively short computation time. The model is fully GIS based and it has an open API which enables us to fully control and interact with the 3DI simulation while it is running. It is completely cloud-based, and you can also interact with the 3DI simulation in a browser. We call this our live site, and I will show you also that this live site in the demo part of this presentation. Well, as I just mentioned, we make use of a subgrid technology, and this technology basically enables us to, with the same amount, with the same number of computational cells, we can provide a lot more detail while still having the same calculation speed. So you can see that very clearly in the animation that is shown in this slide. On the right side, you see, well, both animations are, both simulations are performed with the same number of computational cells, but and have also the same calculation speed. But in the left side, we make use of this subgrid technology, which basically enables us to give much more detail to our flood risk simulations than in comparison to the situation without subgrids. Yeah, so this is very quick on well, Nederland Schuurmans and also our software products, and especially 3DI. Well, this is a very short introduction into 3DI. So if you are interested in this software or in its applications, we will also provide you with some links to information online to this model after the webinar. So you can also look into it, and of course you can also always contact us if you have more, if you want more information. Well, then I'd like to move on to the topic of today, which is the flood barrier. Well, and I think Omar already gave a very nice presentation on the practical applications of these flood barriers. And today I wanted to get a bit more into the technical details and explain to you a bit how it works well in the software. Well, I think these flood barriers are used in our flood risk studies, and I think most people who have some experience in flood modeling will recognize the fact that if you want to build a flood model, it's very important that you capture the levees or other elevated line elements, like for example roads, which are maybe elevated a bit. It's very important to capture these in your model in order to get an accurate and realistic flood model. Well, and to show you how that works in the model, I'm going to use this example. Here on the left, you see a picture of a levee that is located in the northern part of the Netherlands. And on the right side, you can also see the associated elevation map for this area. And actually, this levee is located here. You can see that here runs a river through the landscape, and on the southern part, we have there is this levee which protects the area south of the levee from flooding in case the water levels in the river increase. Well, you can also see in the elevation map that it is elevated a bit, and I'd like to zoom in on this area. So in this case, when the water levels in the river flood, the water will flow will flow from the northern towards the southern part. And say we want to build, we want to make a flood model out of this area. Well, quick evaluation of the local elevation map shows us that the elevation north of the levee are around 0.9 meters above mean sea level, and the southern part is a bit higher, but also not that high, so 1.2 meters above mean sea level. And then the levee in the middle, of course, is a bit higher, so it's about 2.6 meters. Well, if we want to make a model for this area, we have to apply a calculation grid to this area. So it can, for example, look like this. The black lines are the borders of the calculation grids, and the black dots are the centers of each grid cell, a calculation grid cell. Well, say we want to, if you would apply a model in this way, what the model does is it will try for each grid cell, it will look at whether the water can flow from one to another grid cell. So, for example, if the water levels in the river will increase, there will be water in grid cell 1. And in order to determine whether water can flow from grid cell 1 to 2, the model will evaluate the elevation at the location of the border, the cell border between these two grid cells. Well, we know that the elevation there is about sort of 0.9. So, for example, water can flow from cell 1 to 2. Well, and the model will do the same from grid cell 2 to 3. It will look at the elevation at the border between these two grid cells, where the elevation is also not that high. So in that case, if the water increases, the water would in this case also be able to flow from grid cell 2 to 3. So if you would apply the model in this way, the model will not see this levee, and the water can just flow from north to south without being stopped by the levee. Well, of course, this is not what you want. This will not provide you with a realistic flood model. So there are different ways in which you can solve this modeling problem. There are a few options. You can, for example, you could increase the elevation in the entire grid cell 2 towards the maximum elevation in that grid cell. But the disadvantage of that is, of course, that you will lose information on the elevation that is actually that you do have. Another solution is that you can refine the grid, the calculation grid, so much that you will still capture this the elevation or the levee. Well, that you can do that. That will also it could be a solution, but in that case, you will add a lot more computation cells to your model, which makes your model slower. So the last solution for this, and I think in this case it's also actually the best solution, is to apply a flood barrier to your model. And a flood barrier is actually a line that you input into the model that's located at the location of the levee, and that the model uses as information to know which cell borders are close towards a certain height. So you input the model just at the location of the levee, but then the model will translate to which cell borders this applies, and that's always the cell border between the two grid cell centers where the levee is located. So in this case, that will look like this. So in this case, if we do the same experience as we did just before, the water can still flow from grid cell 2 to 3 because this cell boundary is not closed and the elevation is not that high. But in this case, actually the border between 1 and 2, the model knows, hey, there is an obstacle, there is a levee here with a certain height that you input into the model. So water, if the water level in grid cell 1 is lower than this levee height, the water cannot no longer flow from grid cell 1 to 2, and that's actually also what we want in this case. So by applying this flood barrier, you can easily give information to the model on where these levees are located and where water cannot flow from one grid cell to another. Well, a few practical details is that, well, the levee can have different heights, and you can just enter the height of the levee relative to mean sea level. And in case the water level exceeds the elevation of this flood barrier, the water can flow over the barrier. So then there will be flow between grid cell 1 and grid cell 2. A last final remark is that it can still be useful to also apply some refinements in your calculation grid around the location of your levee, but that is more for visualization purposes, because if you would apply the model in this way, you will actually see that around the levee, for example, this entire grid cell can actually flood. So you will, in your visualization map, you will still see some water maybe at the other location of the levee, and this will of course be if you refine your grid, this effect will be less. But it's only for visualization purposes. Actually, the model will work also very fine without local refinements. So that is a bit, in short, like technically how it works if you implement a flood barrier in 3DI. And for now, I'd like to give you a short demo of how this works if you implement this for a model. The model that I'm going to show you is a model for an area of Cape Town in South Africa. And here I went to the live site of 3DI that I just mentioned briefly earlier in the introduction of 3DI. So it's just a website in a browser where you can go to and you can choose which model you want to load. Well, it also always takes some time to load the model. But once it's loaded and the live site is opened, you will see something similar to this. So here you can basically see the map and the location of your model. So as I already mentioned, it is about this neighborhood, which is it's basically a neighborhood that is part of the city of Cape Town in South Africa. This is the name of the model is the Paardenvlei, which refers to the name of the lake here. But actually the focus of this demo site will be this neighborhood. And as you can maybe already see in the area picture, you can see that north of this neighborhood, there is a river. And in the past, this neighborhood has already experienced some floodings when the water levels in the river increase. The water overflows the river banks, and it causes flooding in the southern districts here. To help the municipality with that, we developed a model for this area, which is also very suitable to show you the application of these flood barriers in 3DI. So we built this model. It has a very detailed elevation map, which was provided to us by the University of Stellenbosch, which is located close to Cape Town. In this is the model, but we can interact with the model in this live site by, for example, adding a flow to the river. And in this case, we will apply a flow of 30 cubic meters per second. And you can choose the amount of flow that you want to insert, and you can choose on the map where you want to insert it. So we are going to do it here. And then we can now the river will have a flow, and we can start press to see what's going to happen with the model. Well, what we first see is that the model has some spin up time. So the river is going to fill up, as you can see here. And later on, we will see at which locations the river will first overflow its banks and causes flooding. You can already see that happening here. So here we see that around 12 minutes, the model actually starts to, the river actually starts to overflow here. And I'm just going to pause for a bit. And we also have a tool which is called the side view tool, which you can use to make a side view of your model. Oh, sorry. I have to. Oh, yeah. So here we see the side view, and actually at the you can see the side view of the underlying elevation map. What you can see here is that the left side we have the river. The banks at the right side of the river are not very high, so the water starts to overflow there and start flowing into the neighborhoods in the south. If we would continue with the simulation, you would see that more and more water enters the areas. Well, and if we just saw that the flooding starts around 15 minutes, and the water level here increases to about like a little bit less than 2.5 meters above mean sea level. So, well, this model sort of now helps us to evaluate where let's say the weak points in the system are. And now we're going to start again the simulation. So we will load the left side again to be able just to load for a bit, but then we can start the simulation again. And at this time we will add a flood barrier to the model so that we can see well what the effect of that would be and if that indeed, as we would expect, mitigates the effects of the flood. So again, we have the same area, and well, just like before, we will add a flow to the river at the same location as we did before. But now, as I mentioned, we're going to add a flood barrier. To our model. And you can do that in this way. So here we have the flood barrier tool, and we can choose ourselves how high we want this flood barrier to be in the model. So for example, now we saw that the water level will likely not increase much more than 2.5 meters. So we say like, okay, if we implement a flood barrier with an elevation of 3 meters above mean sea level, we should be safe. Well, then you can easily just draw it on the map. So we can locate it here, for example. We saw that this was the weak point in our system. So we expect if we put the model, if the flood barrier is something like this, that we will be able to mitigate the flooding in this case. Well, if you're done, you just press the OK button. And now you've added a flood barrier to your model. And we can again start the simulation in the same way we did before by pressing play. Well, and again, we see that the model has some spin-up time because the water needs to sort of flow down the river first. And we saw that this used to be the weak point somewhere here. So we will apply, and we will apply a side view tool again in the same place as we did before. And we can now see, like we saw again at around the same time, it started flooding in the previous simulation. We now see here that the water is actually already above the two, well, it's about 2.5 meters now, but we see that it no longer causes flooding here because the water is stopped by the flood barrier that we inserted in the model. What's good to know is that you don't see the flood model sort of located in the side view, but you do see the location where it is because the water is stopped. There. Well, so basically, what we see here is that this is a very nice tool, first of all, to see where your weaknesses in the system are, and then by applying these flood barriers. In this case, it was a very simple case because there was mostly one location where the river overflowed with banks, but sometimes you can have more location and you can see like, okay, which areas are most important to protect, which are the biggest weak points in your system, and you can really easily evaluate the the function of different flood barriers with a model in the live site. So I hope this has been a bit insightful for you. I'd like to stop the demo here. And I think now we still have some time for questions, right, Jonas?
Yeah, let me start up my screen. And
I will maybe stop sharing. Yeah, oh, you're ready. Yeah.
Yeah, okay. I have some questions from the audience. Omar, can you? Yeah, perfect. The first question is for you, Omar. We have some water authorities from the Netherlands also listening in on the webinar. One of the questions is, in the Netherlands, we normally use sandbags. What is the biggest difference, the biggest gain by using a slam dam instead of sandbags?
I think there are a few advantages compared to sandbags. So, for example, sandbags are quite very time consuming if you want to deploy them. In comparison, you need 14 people, 2 hours of time, and then you can build up a barrier of 10 meters in length using sandbags. Compared to, for example, our solution, with just 2 people, you can build up a barrier of 100 meters in 1 hour. The more people you have, more pumps, the quicker you can build up a lengthy barrier. So I think speed is definitely one of them. Our system is also durable, so you can use it for more than 40 years. Compared it to sandbags, yeah, you have to throw them away each time, and it costs quite a lot of resources to get rid of the sandbags as well. So in the long run, our system is a lot, more affordable, and it's more effective. There's a lot of less leakage compared to sandbags.
Okay. The 40 years you just mentioned, this is one of mine. You said that people use it all year long. That is also then, and you can use it all year long, and then it's 40 years. That's the lifespan basically of the barrier.
That's the lifespan. So, well, okay, yeah, and that's the unique thing about our system, because it's made out of EPDM, and that has the properties that it's UV resistant. It's even so that the strength of the material remains the same. Compare that, for example, to a PVC-based system. The strength decreases with each time you use it. And the lifespan of such systems are 8 to 10 years quite often. So the 40 years has been tested. It actually has been tested also with roofing. You know, the EPDM layer is also on roofs.
Oh yeah.
And there it's being used. Yeah, it's a similar, same material.
Okay. Cool. One other one is the projects you did are in quite extreme different climatic zones. What did you learn about the applicability, and what can we learn in the Netherlands from these kind of projects? Because these are all projects abroad or in and not in the Netherlands, as you showed them.
Yeah. Okay. So I think the projects in the Netherlands will be a lot easier. I think the ones we did in abroad were more challenging. First of all, because there's not a data-rich environment like here in the Netherlands. So I think the analysis will be probably we've already the analysis already in place, or we can do it quite accurately here. So from that perspective, it will be easier. I think what we've learned over there is that our solution can be used in a wide variety of circumstances. And you can use it between temperatures minus 35 degrees and plus 120 degrees Celsius in sunlight without damaging. And so the environment in the Netherlands is a lot more friendly compared to those situations. So I think that what we learned about it is that it's applicable in a variety of situations, and I think the Netherlands will be easy compared to those countries. The one thing I have to admit, or I have to say, is the risk of theft or vandalism. That's a risk we always identify during projects. There might be less here, but in some countries, like for example in Lagos and Nigeria, we consider the risk a bit higher if you deploy them. That's why you need to be careful. You might need to have security measures, or you need to make sure that you dismantle them as soon as possible to prevent any theft or damages.
Okay, yeah, that makes sense. But yeah, It's a good addition. Thank you. Last one here is about the FIS tool. Does the FIS use satellite flood records to evaluate impact?
So the tool, what it does, we have readily available data, so the global data sets that are in the system already. I think what the tool also does, it gives you the ability to upload your own data. So it uses, for example, indeed things like population density maps. I think it's from MIT and Meta. But if you have your own population density maps, you can upload them yourself as well. The same goes for land use maps, digital elevation models, and in some instances, I think in the Netherlands, you have the data we have here is a lot better than the global data sets. But also in Lagos, we had, for example, LiDAR data, and we were able to, you can use that data then also in the FIS tool.
Okay, so the LiDAR in Nigeria, you flew in yourself, or some company did that, and then you have high resolution like we have in the Netherlands or the UK or Denmark.
Yeah.
Or...
Yeah.
Okay.
Yeah.
Okay. I have a question for Martine. You showed the flood barrier, and you drew it in with a certain elevation. Does it mean that the flood barrier is going to overtop when this certain when this elevation level is reached?
Yes, so if you will enter a certain height of the elevation, and then that's also like in reality, right? If the water level increases above that elevation, the water will still flow over the barrier, yes.
So you could, well, now this was a very long one, but you could in theory also just use it for any flood barrier, depending on the different height. You just calculate the height and you put it in.
Yeah, basically, yeah.
And can you also prepare these in advance, that you just draw them in together, or can you perhaps use a flood barrier instead of a weir, or how does that work?
How do you mean? Like you can prepare them in advance? Like I don't know.
Yeah, that you do the thing in the live site, and then you can rerun the live site using a simulation template, for example, and then.
Oh yes, yeah, that is very well possible. Yeah, you can. I didn't show that in the demo, but I think when you have a simulation and you added some things, like for example we just did just now with the flood barrier, or with the flow in the river, at the end you can say that you want to save these settings, and if you were starting the live site again, you can just also use these settings to see it again. Yeah, that's.
Yeah. Okay. So you can you can prepare the meeting a bit, and but you can always in
Definitely,
the meeting.
yeah. Now I threw it in all live, but you can definitely yeah, that's possible.
Okay, I have a question. Yeah, I tried to combine them, but now do them separately. The flow over the flood barrier, we are talking about overtopping. But the question is, can you also then use a flood barrier instead of a weir in like a hydrodynamic simulation, or is it different? Do you?
Yeah.
I mean, how you calculate the flow
yes,
over the.
Yeah. Oh, okay. You mean like if the water is overtopped, if you use other equations, then.
Yes.
Well, yeah. Actually, I think there is a difference. Because like if the barrier is overtopped, it will just calculate the flow using the Saint-Venant equations. Well, if you use a weir, we have a special formula for that, the weir formula, for short and broadcasted weirs, where also, for example, the width of the weir is actually relevant. So yeah, there is a difference.
Okay. I think, yeah, the next question is also about friction values, but I think that sort of is implied in this answer, right? In the way you calculate it. I guess the weir formula is more stable in that sense.
Yeah, so if you use a weir formula, you will also have inputs like the friction value that the models should use. It's just 1D, like one value that you use for the weir formula. And in 2D, you could add a friction map with spatially varying friction values. Yeah.
I get a confirmation that this question was answered.
Okay, good.
I have a question for you, Omar. What would you say is the most crucial information you'd need to successfully determine the right location of a mobile barrier?
So all about the flood characteristics and the surroundings. Obviously, the flood depth is important. I think it goes for most mobile flood barriers. It shouldn't be too high. Realistically, if you have a flooding that's 2, 3, 4 meters high, then mobile flood barrier is not the best solution. And in addition, that's why for us it's really important that we also work with local partners who conduct field visits, or we conduct our own field visit, is to get an understanding of the surroundings. Is it accessible? Is the ground surface suitable? We had a project in so the one we did in Lagos, Nigeria. If you look at purely at the analysis at the hydrodynamic model, then there were certain locations where you would deploy the mobile flood barrier. However, when we did the field visits, or when the local partners did the field visits, you saw that the area there was a lot of vegetation, and it was very like a swamp-like area. Okay, then realistically, you cannot deploy a mobile flood barrier over there. So it's these two combinations. So the flood characteristics plus the getting a picture of the surroundings, the environment.
Okay, clear, I think. I don't see any more questions at this moment. If anyone has any last question, then need to type quickly, I guess. So I think we reached the end of the webinar. I would like to thank you both for your presentations. For the people in the audience, we will send you later the information that we also presented today, with also some links to some additional information. If you yourself would like to know more about flood barriers, about slam dam, feel free to contact Omar directly. You don't need to wait. I think his contact details were also in the presentation. And if you'd like to know more about the application, the 3DI, and how to use it, feel free to contact Martine. With that, we have reached the end of the webinar. I would like to thank you all for your attention, and I will stop the webinar. I have found the button for that. Okay, I would like to thank you all.
Thank you.
Thank you.
Meet
Bye.
you soon. Bye-bye.
Thank you. Bye-bye.